In this video, we're going to get a look at a problem that involves differential equations and an opportunity to solve a linear first-order differential equation by the use of integrating factors method. So the first thing that we're going to be asked when presented with a problem like this, and I've tried to make the situation clear through the diagram without having to write down a whole paragraph and have reading the whole paragraph be part of this video. But basically we've got a situation where we've got a tank of, let's just say, water. And there's water flowing into the tank from two sources. There's 8 gallons a minute of pure water flowing in to the tank, 2 gallons a minute of water that contains a solution of 1/2 pound per gallon of salt. There are 80 gallons of water with 40 dissolved pounds of salt in the tank right now, and water is leaving the tank. Always we assume that it's well mixed at the bottom. So we see in this problem, which is something that makes it a little bit easier for us to solve, that the rate of water coming into the tank and the rate of water going out of the tank are the same. But we're going to be asked is to write a differential equation that can be used to solve for a function for the amount of salt in the tank at time t. And we'll go ahead and call that function s. So we're going to say we want s of t. Salt at time t. And so our differential equation is going to need a derivative. It's going to need the rate of change in the salt. So we're going to have to rely on something we know about solution problems like this, and that is that ds dt, the rate of change in the amount of salt in the tank, is equal to the rate that salt is coming into the tank minus the rate that salt is moving out of the tank. And that's just common sense. But we're going to need to further transform this into an equation that's all about the variables t and s, so that we're able to work through our analytical steps. So the rate in this problem is constant. It turns out it doesn't really matter about the 8 gallons per minute of pure water coming in, except for that balances our water in and water out, so that we're constantly having the same amount of water in the tank. But what we do see is that there's 2 gallons per minute of water coming in with 1/2 pound per gallon of salt. So we're going to say, well, we'll just say we have 1/2 pounds per gallon multiplied by 2 gallons per minute coming in. So that's our rate of salt coming into the tank. And we're subtracting from that the rate out, which is not constant. The rate out, we know, is going to depend on how much salt there is in the tank, and more directly on what the salt per gallon concentration is of the water in the tank at time t. So the way that we're going to represent that is we know that S is the amount of salt in the tank at time t, and we're going to divide that by 80 gallons, because there's always 80 gallons in the tank. So we're going to take S over 80 and multiply that by the rate of water going out, so multiplying by 10, and that sets up our differential equation. We can simplify it a little bit. We have ds dt is equal to 1 minus S over 8. This we can recognize as a linear first-order differential equation, but we may rearrange it to make it easier for us to identify the parts of this. So if we write this instead as ds dt is equal to, or sorry, not is equal to, ds dt plus 1/8 S is equal to 1. Then it matches the form dy dt plus P of t y is equal to Q of t. And that's the form that we call a linear first-order differential equation. And this enables us to identify P of t and Q of t, which in turn allows us to find the integrating factor. So we can see that P of t is equal to 1/8. Q of t is equal to 1. And the integrating factor we call mu is equal to e to the integral of P of t dt, which is equal to e to the integral of 1/8 dt, which is actually just equal to e to the t over 8. From here, there's a long justification for the formula we're going to use, but we just need to know this formula. And that is that S is going to be equal to 1 over mu, so 1 over e to the t over 8, multiplied by the integral of mu q of x, so e to the t eighths times 1 dt. And we're able to evaluate this integral fairly easily and then distribute. So let's write that out. We have 1 over e to the t over 8 multiplied by the integral of e to the t over 8 is 8 e to the t over 8 by a simple u substitution, and we have to add the constant of integration. Distributing gives us S is equal to 8 plus C e to the negative t over 8. And now we're ready to use our initial condition to find C. So let's go back up to where we can see our diagram again. We have our initial condition given right here on the diagram. 80 gallons of water containing 40 pounds of salt at time t equals 0. So let's say S of 0 is equal to 40. This is our initial condition for the problem that we're going to come down and use to find C. So we know there are 40 pounds of salt. When T is 0, so we actually have 8 plus C times e to the 0, which means C is equal to 32. And we can finish our solution. S of T is equal to 8 plus 32e to the negative t over 8. This is our unique solution to the differential equation, the function S of t for salt in the tank at time t. And we can use this function now in a fairly simple way to find the amount of salt dissolved in the tank at any specific time. For instance, if we were asked to find how much salt there was after 30 minutes or a couple of hours, we would just be able to plug in 30 or 120 for T. On the other hand, if we're being asked to find how much time it would take before there was a certain amount of salt in the tank, we can plug that in for S and solve for T to find the amount of time. But we don't need to do that in this video. That's fairly straightforward for any student who's learning this material at this point. So thanks for watching this video. Hopefully it was helpful, and check back again for another video to be produced shortly.